All right, that's not too bad, right?
Yeah.
Okay. All right, let's begin this lesson. We're being recorded right now, okay? Everyone say hi to the girls from Kairos. All right, so the first thing we're going to talk about today is something called the secant line. Did you guys talk about that in geometry? Does that sound familiar? Okay. So I put an example up here that shows what a secant line is. And that is a line that goes through, in this case, a circle at two different points. Down on this graph here, the red line is our secant line. The blue line is the blue curve is the actual function that's on the graph. The red line is the secant line, and it intersects it at 2 points. So we can determine the slope of a line, right? We know how to do that. But we can't determine the slope of a curve. Why not? It's constantly changing, right? So way back when, in the 1700s, a couple of these really smart guys ask the question, if the speed of something is always changing, how can you determine what the speed is at any given second? Okay? So if you are getting onto the expressway and you are on the on-ramp, your car is accelerating, right? Because you started from 0 maybe, and you need to get up to 55 pretty fast. Okay? So you look at your speedometer, and it's moving, and it's moving, and it's moving. And if somebody was standing on the side of the road snapping a picture of you as you went by, the question they asked themselves was, how fast is that car going at that very second? And that's what calculus answers for us. Okay? So it's called an instantaneous speed. What is the speed at that instant? Okay? So we can approximate that to begin with. So if you look at that secant line, it's not that far away from that blue curve, is it? No. So if I found the slope of that red line, I could say that that's kind of the slope of that part of the curve, right? If I found the slope of the red line, then we could say that's very similar to the slope of the curve in between those 2 points. Agreed? All right. So let's go ahead and find the slope of this line. So if I look at this point here, that looks like it has a coordinate of 1, 1. And if I look at this point here, that looks like it has a coordinate of 3, 8. So everyone remember the slope formula, girls? You thought you'd never. Why am I learning this, you thought? Okay? For this. Everything you've ever done in math is leading you to this day. Hi, Davia. I do. All right. Oh, live TV. You just never know what's going to happen. Okay, so slope formula. Let's go, girls. The slope formula. Rise over run, right? Remember that? Yes. Rise. I'm just teaching that right now to those freshmen. Morning them, they better remember. Okay, rise over run, which was the change in the y values over the change in the x values, right? Change means the difference. Agreed? Difference means what operation? Subtraction. Okay? So slope, which is represented by m, is the difference in the 2 y coordinates over the difference in the 2 x coordinates. Now, I think I might have shown you this last year, but to signify the difference in something, we can use the Greek letter delta, which looks like a triangle, and that stands for the difference. So we can also write this as the change in y, the difference in y, over the difference in x. Okay, and that notation starts to become very important. This notation, I'm doing this on purpose, becomes very important later on in this unit. Okay, so in this particular case, we're going to fill this in. This is going to be 8 minus 1 over 3 minus 1. So our slope in this case looks like it's 7 over 2, right? Okay. Now, let's write this a slightly different way, okay? Let's pretend that there was no, well, let me leave this here. Let's pretend that there was no scale on this graph, okay? I would have to label this point as x1, y1. And this would be x2, y2, right? I could also label it a slightly different way. I could call this x1, and this is f of x1, agreed? Because isn't y the same as f of x? Agreed? So I could call this x2, and this would become f of x2. Yes? Why, thank you. Okay. In a previous job, I taught kindergartners how to write, so it was horrible. All right. And that's why I'm in a high school. All right, so if we were to use this new notation in our slope formula, it would look like this. Okay, slope equals f of x sub 2 minus f of x sub 1, right? Agreed? Those are still y's. Okay, our notation is changing dramatically, and I need you on board. That's still y. Over x sub 2 minus x sub 1. That didn't change. All right. So now we're going to make a big change. If I decide to just call this point x and f of x, I have to come up with a new name to call this point. So if I'm here, and in order to get here, did I add or subtract to my x value? I added to my x value, agreed? When I moved across here, to get from x sub 1 to x sub 2, my x value increased. Everybody understand that, right? So I can write this new value here as x plus some value. X plus h is what I wrote there. It's hard to see. So x is my original value, and now the new x coordinate has increased by a value of h, right? We're just staying with this right now, okay? Everybody with me on this? Okay? Jackie, doesn't look like you're with me. Okay, what's my x value here when we had numbers? 1. What's my x value here? How many did I increase by? 2. So that's really x plus 2, right? So there's some h value that I used, okay? So that means that my new y value is a function of that new x plus h, right? It's now a function of what my new x value is. My new x value is x plus h, so my y value must be the output of that function, f of x plus h. Whew. Okay? This is math. This is calculus. Welcome to calculus. Okay? All right. So if I use this new, I'm going to use a color. Huh, look. if I use my new way of looking at my points, okay, I have to write my slope formula in a new way. Okay, so let's move on down here and do that. Okay, whew, clean slate. So if I look at what I did, let's go up here so we can see it. That means my slope formula will now be m is equal to my second y value, which is this, f of x plus h, minus my first y value, which is up here, f of x, over my second x value, which is x plus h, minus my first x value, which is x. The slope formula stayed the same. I just changed what I'm calling each coordinate. Okay? I changed what I'm calling each coordinate. Now, I'm going to show you a picture of this in a minute. I wanted to explain it because the picture has all this information on it all at once, and I found it confusing to look at the picture right away. Now, I can't simplify anything up here, but I can simplify the denominator, right? X plus h minus x, well, I can subtract away those, x minus x. So my slope formula in this case is f of x plus h minus f of x over h. So it's just over the change, the increase that we had in x. That's all it is. Okay? You are going to become very familiar with this formula. Okay? The green one. We are going to use it all the time. Yes?
Isn't the green formula just slope?
Yes, it is, but you're going to write it in this format. Okay? You know the slope formula. You've just been able to use x's and y's. Okay? Now we need to use this. Okay? So let's take a look at y, since Olivia just said, why are we doing this? All right. Okay, so gradient in our textbook means slope, right? We know that. Sometimes it says slope, sometimes it says gradient. We are the only country in the world, I understand, that calls it slope. Okay? Yeah, talk about unique. All right. So let's look at this diagram, because you would have freaked out if I tried to explain it before. But it is showing you what I said before. If this point P is x, f of x, agreed? F and the function of x, then this point here increased by h. X plus h got us here, which means the x coordinate of point Q is x plus h, and the function of x plus h. Okay? So this picture makes sense now, but wouldn't have before. So we can estimate the slope or the gradient of this part of the curve just by creating a secant line and finding the slope of that secant line. Okay? So, same picture, and there's the formula, right? We got to that formula already. Same formula that I wrote in green on the other. So the gradient of a secant line is always written like this. It's f of x plus h minus f of x over h. To find the slope of a gradient line, to find the gradient of a secant line, that's what we use. All right. So let's practice. All right, so this example says, write an expression for the gradient of a secant line for the following function, x squared plus 1. What type of graph would that be? A parabola, okay? So if we put a secant line in there, anywhere, we would want to know how to find the slope or the gradient. So let's start with our formula, which was f of x plus h minus f of x, all over h, right? Try to make this as straight as possible for you guys. Well, let's look at the easy part first. What's f of x? So that goes in place of f of x, right? Right? Just as f of x. How would we write f of x plus h? I replace x with x plus h squared, right? Okay, let's take a step backwards, girls. If this is my function, f of 4 is 4 squared plus 1. Agreed? F of h would be h squared plus 1, right? So f of x plus h would be x plus h squared. You're catching on, okay? Get it? So this becomes x plus h squared plus 1 minus our original function, right? All over h. Because you have to subtract the whole thing, because otherwise you'll just write minus x squared plus 1. But it's not minus x squared plus 1, it's minus x squared minus 1. Okay, so I put the brackets so that you remember to distribute the negative. Your textbook does it too, because they know you won't distribute the negative too. All right, so let's simplify this. X plus h times x plus h, right? This is not x squared plus h squared, and if you write x squared plus h squared, I'm going to go bang my head against the wall, okay? It is x plus h times x plus h. Okay, so we have to double distribute, but let's get into the habit, because you're going to do this a lot, of remembering that it's just this, right? Remember when we did those fast ways to multiply or square a binomial? But you can go ahead and do it the long way. I'll wait. You're going to come up with that answer, right?
The plus 1 is from the plus 1 on the
Oh, I'm sorry. I did it wrong. Thank you. H squared. Sorry. Ah, Mrs. Bennett. Got it. So now I get to go put that in for x plus h squared. This becomes x squared plus 2hx plus h squared plus 1. Now my plus 1 came in, Samantha. And I have to distribute my negative, minus x squared minus 1, and we're still all over h. So let's see what we can simplify. Oh, look, x squared minus x squared, that's gone. 1 minus 1, that's gone. And that looks like all we got. So we're left with 2hx plus h squared over h. I have an h in this term, right? I have an h in this term, and I have an h in this term. Let's get rid of those h's. Okay? I have an h in each one of these terms. If that confuses you, you can think of it as this way. Remember, we can always separate a fraction like this. So these h's cancel out, and one of these h's cancels out. So we are left with 2x plus h. So that's the equation of the secant line, wherever you decide h is. How far away from the original x do you want to go? And this will give you the slope, or the equation of that line. Okay, so if your first x value is 8, and you decide to go 2 away, your h is going to be 2. Okay, so it's going to give you, yes, Emily?
Okay, can I go? I was just like pointing out
Yeah.
what I'm trying to say. Okay, so just so I make sure, like, I understand what's going on. So this is technically, like, from before, this is y1 and this is y2.
Mm-hmm.
So since f of x is y, that's why that you just bring that there.
Mm-hmm.
And then since this is y2 and you're going along the x-axis, you have to add an h because that's the difference between the two x's.
H is the difference, yes.
Okay, so how come you put it in, like, how come it wouldn't be x squared plus h? Like, how come you put it
Because
before?
Because here, I changed this x to x plus h. So I substitute x with x plus h. Just like here, I changed x to 4, so I substitute 4 in for x.
Okay.
I changed it to h. So I'm really just plugging in, substituting in for x. Okay? So now, I could find the equation of any secant line. Any secant line, okay? All right, so why do we care? Here's why we care about this. Okay, I'm not going to tell you why we care yet. We're going to do some practice. Sorry, practice next. All right, so we're going to do some practice. We're going to do one more together. We'll do number 1 together. This is exercise 7C. We'll do one more together, and then you're on your own for 2 and 3. So, again, our formula is f of x plus h minus f of x all over h. So my function is 3x plus 4. So in place of x, I write x plus h, right? So this becomes 3 times x plus h plus 4. That's the first one. Minus 3x plus 4, which is my function, f of x. All over h. So let's do our math. 3 times x, 3x plus 3h plus 4 minus 3x. Oops, see, I did it. Started to write plus. Minus 4. I have to distribute the negative, right? All right. What? Wait. You think you understand it, or you have a question? Okay, Myra, you have a question? Okay, so f of x equals this. If I had f of 6, I would write 3, and I would replace x with 6, right? That's how function notation works, right? So if I have f of h, I would replace x with h, right?
Yeah.
If I have f of x plus h, I would replace x with x plus h, right? Whatever's in the parentheses tells me what to plug in for x. All right, so let's see what we can eliminate. That cancels out, and that cancels out. And now I am left with 3h over h. So my answer is 3. Okay?
Did you write like f of x equals 3?
Nope, this is f of x. Write the expression. So it's an expression, not an equation. So right now we would just write 3.
Oh, okay.
All right, so try number 2 and number 3.
You don't put I equals 3?
No, because this is an expression for the secant line, okay? Because it's not, well, let's just leave it at that.
Okay.
All right, so I'm going to pause this. All right, you girls at home, you work on this now.
Second one?
All right, so let's try these now. So, yikes, too much in my hand. So for number 2, we're going to say f of x plus h minus f of x over h. So so that is going to be 2 times x plus h squared minus 1, all minus 2x squared minus 1 over h. So 2 times x squared plus 2xh plus h squared minus 1, still in brackets, minus 2x squared plus 1. So now we can distribute our 2x squared plus 4xh plus 2h squared minus 1 minus 2x squared minus 1. All right, so this will cancel out.
Still plus one.
I'm sorry, plus 1. Thank you. This will cancel out. And now we have 4xh plus 2h squared. Oops, that's all over h, sorry. My fault. Yikes! All over h. So 4xh plus 2h squared over h. One of the h's. 4x plus 2h. Got it? All right. Do number 3 together. Okay. So f of x plus h minus f of x over h. So this is x plus h squared plus 2 times x plus h plus 3 minus
The plus two, I know.
x squared plus 2x plus 3 all over h. Okay, so everywhere you see h, you have to plug in x plus h, right? All right, so x squared plus 2xh plus h squared plus 2x plus 2h plus 3 minus x squared minus 2x minus 3 all over h. X squareds will cancel out. 2x. And I think that's it. The 3's, thank you. All right, so we've got 2xh plus h squared plus 2h over h. One of the h's, h, 2x plus h plus 2. Okay? Yes?
I don't know why you lost me like at the very beginning. Can you explain that first bracket?
Okay. Here's our function, right? What do I plug in place of x here?
X plus it.
Right.
Oh.
X plus h squared. Right? What do I plug in for this x?
X
2 times x plus h
plus
plus 3. I just replaced both of the x's with x plus h. Got it?
Yes.
Okay. The rest is just algebra. Okay. We good? We are. Let's move on. Okay, so for a minute, let's go back to that original diagram. Now, this secant line that we have there, it's not exactly representative of my curve, but it's close. So let's take a look what would happen if I decided to put my secant line here. Okay. And if I found the slope of that line, do you think it's would be a better representation because it's closer to the curve? Yeah. Don't you think? Look how far away this red line was. Now that line's even closer. Right? Well, what would happen if I made it even closer to my original point? It's getting even closer. So, what if I went right here? I can't draw that one, okay? It gets even closer and closer. So, as this point, which is x, h away from x, right? As h gets smaller, I move closer and closer to x. Agreed? Okay? Till eventually, I am left with, let's see if you guys remember what this line is called. A point that is, a line that is just going through the point, and that is the only point on the curve that it touches. What do we call that? When a curve just touches one, when a line just touches one point on a curve? Tangent. What does tangent mean? What? It intersects that point and only that point. So that makes sense to us that that would be the best line to find the slope of, right? You don't know another point on that curve, do you? Okay? So what was happening to our h value? It kept getting smaller and smaller, right? The closer I drew the line, the smaller it got. Okay, so here's just a reminder of what a tangent is. Okay? You learned that in geometry. So that would mean, oh, here's an even better picture. I forgot. Look at this picture. There we go. Okay? So, secant line is in blue, and as this point moves down the curve, you will eventually get to the tangent line. Okay? So what we found, well, not we, some very important math people, I just included myself, is that if you could find the slope of that line, you would find the instantaneous speed of that car at that point in time. Okay? Olivia?
Would you use that line and find other points on that line?
Well, we don't even have to do that. Okay? Let me make sure I'm right. So, this is not good because I covered these. Yikes, look, that's from my sweaty palm. Okay. We have a special name for that tangent line. It's called the derivative of a function. That tangent line is called the derivative of that function. So basically this is saying if we slide this point down close enough, it becomes the tangent line. Okay? Let me get it to look rubbery. Come on, I can do it. All right. So basically why I covered those up, thinking that if I had the smartboard, I would move them. I know it's back there. So h is getting smaller and smaller and smaller as my secant line approaches my tangent line. Agreed? So that means that h is approaching 0, right? Yeah, we're getting there, girls. You're getting it now. So that would mean that I needed to find the limit as h approaches 0. It does. See, it all comes together. I need to find the limit as h approaches 0 of that slope formula. And that gives us the tangent line. Okay? So let me give it to you in better looking writing. Oops. There it is. The function defined by the limit as h goes to 0. That's hard to see. All right, I'm going to zoom in. Ready? This is the zoom by hand because this is the cheap document camera. Zoom, zoom, zoom. There we go. Okay. Yes.
Oh, you actually have to lower it.
Yes. The cheapy one. I had to lower it by hand. Okay? So the limit as h approaches 0 of the slope of that line. Okay? That will give us, and it's called the derivative, and that gives us that tangent line, which is which is the slope at that point and only that point. If we picked a different point, you'd have a different tangent line, right? Agreed? Let's go back to this diagram, right? This is a tangent line here, but if I picked this point, there's a different line that's tangent there, right? Yikes, that's terrible. Okay. So every point has its own tangent line. Yikes. That's really close. That's when I like to put my diamond down there. Look at that. Woo, looks really big. Okay. So every point has its own tangent line. Every point has its own tangent line, right? So that's how you find the slope of every point on a curve, by finding that individual tangent line, by using this handy-dandy formula called the derivative. Okay? So when you're finding the derivative of a function, you are finding the slope at a specific point on that curve. So let's look at some of the lingo here. Okay? Notice how this has f prime. Notice the apostrophe? That is the notation for derivative. Okay? So the function might be 2x plus 8, but we would write the derivative. So you would pronounce this as the derivative of x as the limit as x approaches 0 of this. Or dy over dx. What do you think the d stands for? No.
Delta.
Delta. Remember? I said I did this for a purpose. You can also write this as dy over dx. Okay? It all comes full circle. All right, so let's look at what this says. F of x is read as the derivative of x, or f prime of x. Dy dx is read as the derivative of x with respect, derivative of y with respect to x. Or you say dy dx. Okay, when you say dy dx, that means dy over dx. Okay? Because we did this. Slope is a change in y over the change in x. We can write it as delta y over delta x, or dy dx. See? Not so tough, right? We're good? Okay, so let's do another example together. Example 4 says, find the derivative of this function, which means you're finding the slope of the tangent line. And hence, what does hence mean in IB? No. And hence, that's a signal. Use the information you just got to determine the next answer. Hence means you must use the answer you just got in your working for the next answer, okay? There's also hence or otherwise, which means you can use what you did, or if you know a better way, go ahead and do that, okay? Hence or otherwise. This is hence, meaning whatever you find, you have to do.
So you would plug in 3 for x in the answer that you got?
Yes. So we're going to do this together, girls, okay? So, we already did this, right? Go back to example 1. What did we find for the derivative of this? No. The one that's 2x plus h, right? Example 3, right? Was it example 3?
It was like the first or second.
All right, I will find. All right. Right? So we already know that, so let's not do the work all over again. So that means the limit as h approaches 0 of 2x plus h. That's our derivative. There's no equals.
And then x becomes 3.
No, hang on, girls. All right. As x approaches 0, I'm sorry, I keep saying x. As h approaches 0, this value gets smaller and smaller and smaller and smaller and smaller, right? So eventually, if it got to 0, again, a limit doesn't get there, but if it got to 0, we would write this as 2x plus 0. If it hit 0, that's where it would be. Agreed? So that means we would say that the derivative, in this case, we want to find it when x is 3. The derivative